Okay, so, oh, wait, I want to use. Okay, so welcome back. I hope you enjoyed the midterm and learned from it. So we will, we're going to finish grading the midterm by Monday, and you'll get your scores and so on back then. I'll post solutions tomorrow, and I'm also going to send out a survey later today. So, okay, let's continue. So this is lecture 11. And roughly, before I start, let me just roughly say what the plan is for the next 10 lectures. So we're going to have we're going to have 2 lectures on induction. That's chapter 5. Then we're going to have 3 lectures on counting. That's chapter 6. And then finally, we're going to have 5 lectures on probability, which is one of the most widely useful things that we learn in this course, how to rigorously reason about uncertainty. And today I'm going to tell you about induction. So there are really only 2 topics today. The first is the principle of mathematical induction. There's really only 1 topic. The second topic is a variation on it, which is called strong induction, which is not really a fundamentally new thing, but it's a different way to apply it. And roughly this is section 5.1, and this is section 5.2. Okay, so let me start by talking about induction. So it's basically a new inference rule and proof technique. So far, what have we done? The basic proof structures we've looked at are, well, okay, if you want to prove for all x p of x, then the proof looks like, okay, assume x is arbitrary. And then do some stuff, and then prove p of x. And the conclusion is that, okay, for every x in the domain, p of x holds. And we also looked at how to prove another type of quantified statement, which is there exists x so that p of x. And the structure of a proof like this, if you're going to do it directly, is just, well, you just produce some x such that p of x is true, right? So you produce x such that p of x holds. And mathematical induction is a new inference rule. Let me tell you what the inference rule is. So it's a new inference rule for proving a very specific type of statement. For proving a statement of type for every positive integer n, for every n in the positive integers, p of n. So this is the type of statement that you can prove using induction. And p of n is now a propositional function. Here. So it's a propositional function where n has to be a positive integer. That's a key feature of this. And let me tell you what the rule is. The rule is if p of 1 is true, and for every integer k, for every positive integer k, p of k implies p of k plus 1, then the conclusion is that p of n is true for every integer n. Okay, so it's I mean, it intuitively makes sense. I'll say a bit more later about how to formally derive this. It follows from the well-ordering principle, the well-ordering, which is an axiom. And you know, what does a proof based on this inference rule look like? So let me just show you the structure of the proof. So here's what a proof by induction looks like. So if you want to prove this statement for every positive integer n, p of n, so first you usually just say you're going to do induction. So you say something like, we proceed by induction. Just to tell the reader that that's what you're going to do. And then there are two things you need to do, right? You need to prove P of 1. So that has a name. That's called the basis step. And in this step, you just prove P of 1. So that's the first item here. This is the basis step. And then usually the more interesting step is called the inductive step. Where you prove the second implication. And this has to hold for every integer k. So what's the proof? What does the proof of a statement like that look like? What's the first line?
For all.
Right, but in the proof, how do you actually, prove a for all statement?
Wait, first you assume that like P of k is true for arbitrary k?
Yeah, so you have to do that in the right order. So first you assume k is arbitrary. So you assume k is an arbitrary positive integer. And then you now assume P of k. So you assume P of k. And now you do some stuff and you show P of k plus 1. And now you have concluded that for every k, P of k implies P of k plus 1. And so that concludes the proof. So you conclude for every positive integer. So this is now outside the inductive step, P of n. Okay. Now this is a bit abstract. Let me show you an example just to make it clear. Any questions about this that I've said so far? Okay. Okay, so let's do an example. So I'll just start here. So suppose I want to prove that I want to prove the formula for the sum of powers of 2. Okay, so suppose P of n is the statement, the summation from I goes from 0 to n of 2 to the I is equal to 2 to the n plus, or 2 to the n plus 1 minus 1. Right, this is a proposition indexed by positive integers. And suppose the goal is to show that this is true for every n. For every positive integer n, this formula is true. Sorry, I equals 0 to n. Okay. Now, what's the proof of this going to look like? Well, okay, this is an infinite family of statements indexed by the positive integer, so I'm going to use proof by induction. So what's the proof? So first you say we proceed by induction. Or you can just say by induction as a shorthand. And now again, there are two ingredients, right? There's a basis step and an inductive step. So what's the basis step in this particular example? Well, it's the statement P of 1, right? So we have to show P of 1. So let's, just since this is our first example, let's be totally explicit and say we will show P of 1. And what is P of 1? Well, it's the proposition you get when you plug in n equals 1. So that is just 2 to the 0 plus 2 to the 1 equals 2 to the 2 minus 1. Or, I don't even want to say IE. I mean, that's pretty much the proof. So let me just say, observe that 3 is equal to 2 to the 0 plus 2 to the 1, which is also equal to 4 minus 1. I mean, okay, this is a I guess this is a weird way to say it, but we're just saying both of these things are equal to 3. Okay, so P of 1 was easy, right? I just proved the statement for n equals 1. So any questions about the basis step?
I have a clarification question. Should the summation be 2 to the I is equal to 2 to the I plus 1 minus 1? Or is it 2 to the n plus 1 minus 1?
No, it's 2 to the n plus 1 minus 1. Because so here
Okay.
I and n are playing very different roles, right? So n is the number of terms in the sum. And I is just a running index in the summation notation, saying I look at I equals 0, I equals 1, I equals 2, all the way to I equals n. So just to clarify, what does this notation mean? This, I equals 0 to n, 2 to the I means 2 to the 0 plus 2 to the 1 plus 2 to the 2, dot, 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 up till 2 to the n.
Okay, I see. Thanks.
Yep. So then, okay, we've done the basis step. So now, as usually, the more interesting thing is the inductive step. So now we have to assume k is arbitrary. So assume k is arbitrary. And now I'm going to assume P of k holds. So I'm going to assume. So what is P of k? What does it say? Well, it says that the sum of the powers of 2 up to k. Sorry, this is a little hard to read. Is equal to 2 to the k plus 1 minus 1. So this is where I'm assuming. So by the way, this has a name. It's called the inductive hypothesis. So when because when I'm putting this on the table, right? So it's a hypothesis. I'm assuming this to be true. This is called the inductive hypothesis. So in this case, the inductive hypothesis is now this statement, which I'm assuming to be true. And now I need to show P of k plus 1. So I don't know, what should I do? So this is now where the usually the creativity comes in. How do you establish P of k plus 1?
You could try multiplying each side by 2.
Could try multiplying each side by 2. Okay, that's an interesting possibility. There's something, okay, that eventually works, but it's a little more complicated. It's a good idea, but anybody have a sort of simpler idea?
We can just like add 2 to the k plus 1 to both sides.
Yeah. So now observe that when you add 2 to the k plus 1 to both sides, you have I equals 0 to k, 2 to the I plus 2 to the k plus 1 equals 2 to the k plus 1 minus 1 plus 2 to the k plus 1. But now what is the left-hand side of this equal to?
The summation from I to k plus 1.
Yeah,
To the I.
this is just a summation from I to k plus 1. I goes from 0 to k plus 1 to the I is equal to this. So I peeled off the last term. And really the content of this is, I found this quantity that I can analyze using P of k inside this sum. And now, okay, now what's the right-hand side equal to? Well, it's 2 times 2 to the k plus 1 minus 1, which is 2 to the k plus 2 minus 1. Or to make it very clear what I'm doing, it's 2 to the k plus 1 plus 1. Right? So this was the creative step here. And some of the content of this was that I related what's happening for the sum with k plus 1 terms to what's happening for the sum with k terms. But anyway, now I've proven p to the k, right? Right? So I assumed p to the k and I proved p to the k plus 1. And now that's it, right? That completes the inductive step. So you could either say this completes the inductive step, or you could just end the proof. Okay. Now, any questions first before we say anything about this?
For the basis step, could we pick any number?
No, you have to pick the smallest number for which you want to show the statement. Now let's explain why. So let's let's draw a picture of the implications, right? What a proof find, if you really unroll what it's doing is, first you prove p of 1, and this you prove to be true in the base case. Then you prove that this implies p of 2. So you know that p of 2 is true. Then that implies p of 3. And that implies p of 4. That implies p of 5. And so on. It goes on forever. So you have to start at the beginning, because there is actually a direction to how this is going, right? So this is where the base case or the basis step. Okay, so some people call this a basis step. Some people call this the base case. I actually prefer calling it the base case. I may occasionally call it base case. So let me just mention that here. Okay, so P of 1 is the base case. That's the beginning of the induction. And then in each of these arrows, how do I know each of these arrows is true? Because of the inductive step. The inductive step is actually proving infinitely many implications. Right? So the first implication is the inductive step with k equals 1. The second implication is the inductive step with k equals 2. But we proved it for every case, so you can just keep going forever. That's the beauty of induction. You get to prove infinitely many statements just by proving the base case and the inductive step. Does that answer why you have to start at 1?
Yeah. Well, I was having trouble. Why not 0?
Oh yeah, no, sure. You could in principle do this with 0. Yeah. This is just a convention that we start with the smallest number. So yeah, in general, if you want to show this for some set of integers that has the smallest number, then you start at the smallest number.
Okay, thank you.
But you can't do this for like all the integers because they don't have a smallest number, right? And okay, let me mention two metaphors for this that I don't know, are mentioned in the book. I don't know if they're useful. One is that it's kind of like a ladder where, okay, there's a ladder and you start at the lowest rung, which is P of 1, and then you slowly climb the ladder. And the inductive step is telling you how to take a step. And if you know how to take one step, you can keep going forever. And the other metaphor is that it's kind of like, it's like dominoes. Like suppose these are dominoes and you knock one over, well, then it starts knocking the next one over and so on. But you can't go from P of 1 to P of n directly, right? You have to have this whole chain of implications. So you know, let me make some remarks about this. Which are related to the question Javier just asked. So remark one is that this is, you can prove this is true using the well ordering principle. Okay, so the validity of induction is actually equivalent to, but in particular follows from, the well ordering principle. And I won't belabor it here, you can read about it in the book, but basically by considering the following set, it's a set of all positive integers such that P of n is false. And why is this, you know, and this set will, why this has a least element by the well ordering principle if the set is non-empty. And you show how do you show the set is non-empty? By proving P of 1. Oh, sorry. You assume, I've got it wrong. You assume for contradiction the set is non-empty. I mean, you want to prove the set is empty. And then you induction, and the induction follows from this well ordering principle. The second remark I want to make is that there is something special about the integers, right? So you can't prove for every real positive real number P of x using induction. Okay. Can anybody think of intuitively why you can't do that?
What would the next step be?
Yeah, what would the next step be, right? There is no next real number.
But for integers, it's discrete.
Yeah, exactly. So this is where the discrete comes in. Integers are discrete, so there is a next integer. And at a more formal level, as you saw in the midterm, there's no well ordering principle for the positive reals. So this is where discreteness comes in. You need the discreteness of the integers for induction to work. Okay, so let's do one more example, which will highlight a very curious feature of induction, actually. So here, I'm actually going to do the example and a modification of it. I'm going to consider the statement P of n is, so actually I'm going to define a quantity first. So so let Sn be the sum of the first n odd positive integers. Okay, so in summation notation, Sn is the sum as I goes from 1 to n of 2 times I minus 1 plus 1. Okay, the ith odd integer is 2 times I minus 1 plus 1. So just for example, S1 is just 1. S2 is the sum of the first two, odd positive integers. So that's 1 plus 3. S3 is 1 plus 3 plus 5, and so on. So any questions about the definition of Sn?
It seems like we could prove using induction that you can write the odd integers like this. Given that, how should we determine when we need to prove that we can, like, it seems like induction is pretty powerful.
Okay, I see
And
what
I'm
you're saying.
wondering when we don't need to use it and can take things that we now can prove.
Yeah, okay, so let's take this as an assumption that this is the ith odd integer. Okay, it is, we won't prove it right now. You can prove it by induction if you want. Let's take that as an assumption that that's the ith odd integer. So I haven't stated what I'm going to prove yet. So now the claim is that Sn is a perfect square. For every n bigger than 1, Sn is a perfect square. It's certainly true in the examples we looked at, 1, 4, and 9. But this is actually true for every positive integer. So let's try to prove this. So for now, I would say at the beginning, always be very clear about what your P of n is. So let P of n be Sn is a perfect square. Sorry, is somebody writing on the screen? Let me disable annotations. Sorry, can you erase what you wrote on the screen? I don't actually know how to erase it. Justin, I think, wrote this on the screen. Okay, fine. I guess I can erase it myself. Okay, so we're going to prove this by induction. So what's the basis step? Basis step is that S1 equals 1 is a perfect square. So we just state that that's true. 1 is a perfect square. Inductive step. So let K be arbitrary. And now assume Sk is a perfect square. And now we do the same thing. We want to say something about the sum of the first k plus 1 odd integers. So observe Sk plus 1 is Sk plus one more number, which is what?
K plus 1?
Yeah, the k plus first odd integer, which is 2 times k plus 1 minus 1 plus 1, which is now Sk plus 2k plus 1. And now I want to use the inductive hypothesis, right? Let me erase this line since it's kind of just annoying and we'll end up reformatting a little bit. We add a little bit more space here. And you know, when I assume K is a perfect square, that means something, right? It means that Sk is equal to some m squared for some integer a, right? So you know, so really well, okay, let me just write it here. And something is a perfect square, I can put something on the table, right? And what is that? Well, it's some number m. So choose m such that Sk equals m squared. And now I have that this is m squared plus 2k plus 1. Okay, why is that a perfect square?
It's m plus 1 squared.
Well, it's not, right? Because m is not the same thing as k. Actually, we're kind of in trouble, right? It's not true that for every m, that thing is a perfect square. You know, I could take, I mean, it's true when m is equal to k, this is a perfect square. But in general, there's not much you can do with that expression. It's not true that it's a perfect square for every m, actually. So we're kind of stuck here. So this brings me to a counterintuitive property of proofs by induction. The counterintuitive property is it's sometimes easier to prove something that's stronger. Okay, so what I'm going to do is I'm going to try to repeat this proof with a stronger induction hypothesis. Okay, so here's another attempt. And here I have a stronger induction hypothesis. So again, the claim is the same. Again, I'm going to prove something even stronger. So claim prime, which is that Sn for every n bigger than or equal to 1, Sn is equal to n squared. This is a strictly stronger statement. So it sounds like it should be harder to prove, but it's actually going to be easier to prove. Let's repeat our steps. So here now, you know, what is P of n? It's just Sn equals n squared. And now the basis step. So P equals 1 is the same as the other side. And now the inductive step. Turns out to be a little different, right? So let k be in z plus and assume P of k. Okay. And P of k is that Sk is equal to k squared. And now again, now we repeat the same thing. You observe that Sk plus 1 equals k squared plus 2k plus 1, which is k plus 1 squared. And you can just write as desired here. And that completes the inductive step. So why did the right-hand side work, whereas the left-hand side failed?
Extra variable.
No, there's no extra variable.
We had more information to work with, because like because we were trying to prove something stronger, it meant that our induction hypothesis also got to be stronger.
Exactly. So our goal was to prove something stronger. When we assume P of K in the inductive step, we have more to work with on the right-hand side, right? So this is the key step, but the key thing is that on this side, Sk is K squared. Whereas on the left-hand side, Sk is just some M squared, and we don't know what M is. And that's why on the left-hand side, we got stuck. Because we don't know what M is. But if we assume more, we have more to work with during the induction. And so we can prove something stronger. So this is a weird feature of inductive proofs, that sometimes it's easier to prove something stronger. This has happened to me many times in my life, where you're trying to prove something it's really, really hard, and then you make it even harder, and then it becomes easy. Because you get a right inductive hypothesis. So the whole art in inductive proofs is choosing the induction hypothesis. So any questions about this? It's kind of an important point. So I should add a remark, by the way. This is actually the very first proof by induction ever done in the 1500s, historically, apparently, that the sum of the first n odd integers is a perfect square. Okay, so any further questions about this?
Can you explain where the observe that step came from?
Yeah, so I guess I skipped a step in the observe that step. I had said, well, Sk plus 1 is equal to Sk plus the k plus first odd number, right?
Right.
So by the inductive, yeah, okay. What I used here is the inductive hypothesis. I used that I know that this k squared is equal to Sk by the inductive hypothesis. Maybe that's what you were missing.
Yeah, no, that makes a lot more sense. Thank you.
Yeah, sorry, I skipped a step. If you look at what's on the left-hand side, I said Sk plus 1 is equal to Sk plus 2k plus 1. Same on the right-hand side. But now the beauty is I know more about Sk. I know that it's k squared, not just something squared. Okay. Okay, so you can use proof by induction. So far, we've proved a bunch of things about numbers. You can use this technique to prove things about things other than integers. So here are some examples. You could have P of n. This could be any of the things we've seen above, like some statement about, a sum of a bunch of numbers, or it could be some statement like, 2 to the n is less than n factorial. It could be an inequality. Or it could be if a set has n elements, then its power set has 2 to the n elements. Or it could be some statement about divisibility. It could be that 3 divides n cubed minus n. And it could really, we're going to do something in a moment, which is kind of outside the realm of what we've done in the class so far. It could be a statement about a fairly complicated object as well, as long as it's precisely defined. So let me now let me now show you an example of that. Okay, so here's and okay, actually, let's take a 1-minute break since we're approaching the usual time when my screen freezes, and we might as well take a break. So any questions come up during the 1 minute break? So someone is saying you have a hard time conceptualizing this. Any specific question? It seems like magic. It kind of seems like magic. So I agree. The first time I saw this, it seemed a bit surprising to me that you could do this. Okay, let's just do another example. Maybe that'll make it clearer. You'll be doing many examples on the homework. So here's kind of a puzzle. The puzzle is, can you perfectly tile a 4x4 chessboard?
Are you trying to write something?
Oh man, really? My screen crashed just as soon as I got back? Okay, fine. I'll be back in a moment. Okay. Can you see now? Yeah. So the puzzle is, can you perfectly tile a 4x4 chessboard? Let me draw a picture of it. So it's not, it's smaller than a real chessboard. So it's like, with triominoes. So triominoes are like dominoes, except they have 3 squares. So they look like this, or rotations of that. Or sorry, I guess I already did this one.
So an L-shaped piece.
It's an L-shaped piece, yeah.
No, like vertical.
No, so you could have this. Okay, so perfectly tile means every square is covered and there are no overlaps. So here's a puzzle. So I don't know. Anybody have any? You think you can do that?
Wait.
If the
No,
triominoes
I don't
are
think you can.
3, how would you fill in 16 squares?
Yeah, it's a great point. Right. So this is the question. And the answer is no, because each triomino has 3 squares, and that doesn't divide the total number of squares, 16. Right? If you could do this with some k triominoes, you'd have 16 equals 3 times k. This is not true. Okay, fine. So now let's ask a modified question. Can you perfectly tile a 4x4 chessboard with 1 square removed? So let's remove some square from here. Let's say this one. There's no more divisibility problem because there are 15 squares. So if you can do it, you should be able to do it with 5 triominoes. Anybody see how to do it?
Can I ask a question about the triominoes? The option, you can't have 3 squares vertically. That's
No,
like
no,
a
no,
stick.
no, no, no,
That's
sorry,
not an
sorry.
option?
They're all L-shaped. They're all L-shaped.
Got it.
Okay, so this is not obvious. I don't expect this to be obvious. But what I'm going to do is I'm actually going to prove a theorem that's kind of quite, I think, stunning. The theorem is the following. For every positive integer n bigger than 1, every 2 to the n times sorry, I should make this clearer. Every 2 to the n by 2 to the n chessboard with one square removed, any square, can be perfectly tiled by triominoes. Okay, so this is, I think, quite amazing. It's saying that you can give me a, 2 to the 10 by 2 to the 10 chessboard. That's like 1024 by 1024 chessboard. Remove one square, and I can perfectly tile it using these triominoes. So in particular, you can, for the n equals 2 case is 4 by 4. So this theorem implies that you can do the n equals 2 case. So we're going to prove this by induction, but any questions about the statement before we do that?
Would the base case be like, would we just do n equals 1, so it's a 2 by 2?
Yeah.
Okay.
So let's do it, right? So let's write the proof. So the proof will be by induction. Well, okay, but maybe since we're starting out, let's just say what P of n is, right? So let P of n be every 2 to the n by 2 to the n board with one square removed can be perfectly tiled.
Professor, is it any square on the chessboard, or is it
Any square.
Okay.
So really, what we're describing is a very large number of possible boards, right? Because you can remove any square. So this is P of n. So we proceed by induction. So what's the base case? Well, if n equals 1, the board is, there are only 4 possibilities. So a 2 by 2 chessboard looks like this. And you remove one square. So you either remove this, or this, or this, or this. And each of those can obviously be tiled with one triomino, right? It's actually just equal to the shape of one triomino. Any questions about the base case? Okay, now let's do the inductive step. So now we have to, again, follow the rule, right? So let k be an arbitrary integer. Okay, and now assume P of k. So that says that every 2 to the k by 2 to the k board with one square moved can be perfectly tiled by a triomino. Now we will show pk plus 1, right? So now what do we have to show? What's the next line? We have to show pk plus 1. What do we have to put on the table next?
We can tile basically any 2 to the k by 2 to the k board with one trinomino removing. And we can notice that like a 2 to the k plus 1 by 2 to the k plus 1 board can be split into 4 2 to the k by 2 to the k boards.
Yeah, so you're right, but I was asking for something much more basic, which is just first, let's assume we have a board, right? So let B be a 2 to the k plus 1 by 2 to the k plus 1 board with one square removed. Okay, because we have to prove something about all such boards, right? There's a hidden for all in here because we don't know which square is removed. So let's draw a picture here. And now I'm going to do what you said, which is the clever idea here, which is not obvious, which is I'm going to partition this into 4 boards of size 2 to the k. So partition B into 4 boards of size 2 to the k. So I mean, you know, the picture here is that the side length of this is 2 to the k plus 1. So if I divide it by 2, the half side length will be 2 to the k, right? And if I split each side in half, I'm going to get 4 boards. And again, another good principle I'm trying to convey in this course is give everything names. So let's give these boards names: B1, B2, B3, and B4. So let's just call these. This is B1, this is B2, this is B3, and this is B4. Okay, so now there's one square removed, right? And that could be in any of the boards, right? We don't know where it is. So now I'm going to do something which is in itself an observation, which is I'm going to say without loss of generality, assume the missing square is in B4. Now, why is that without loss of generality?
Because it can be any of B1 through 4.
Okay. Right, but why are they all in some sense equal?
Because
rotate.
You can rotate, exactly. Because the set of triominoes doesn't change if you rotate the board. Right? Can rotate the board. So this is the case. So right, I don't know where the missing square is exactly, but by rotating it, I can make sure it's in B4. Okay, so I've already done some creative stuff here, which is partition the board into 4 boards. And then this is actually kind of creative. Assume that the missing square is in B4. So I for free got this slightly more grip on where this missing square is. And now I haven't applied the inductive hypothesis. How am I going to apply the inductive hypothesis?
E4 can be tiled with trinominos.
Okay, so by the inductive hypothesis, B4 can be tiled, can be perfectly tiled. Okay, but what about the other ones?
if we put a triomino in the center, it's almost like we have one piece removed from each of the three other boards.
Yeah, it's not just almost like, it is exactly like that, right? So this is the real clever part of the argument, which is place a triomino T, let's give it a name, why not? At the center of B with one square in each of B1, B2, and B3. Okay, so this triomino T is going to look like this. This blue triomino. And now what's nice about this? Why is this like so great? So hint, I'll just put these X's here.
Oh, that means that in each of these squares, each of like B1, B2, B3, like one square is removed. So that's like the previous case.
Exactly, right? So now observe, or let's just give it a name. So let B1 prime, B2 prime, B3 prime be, let's see, how should I describe it? I want to describe it very carefully. Yeah, be just the previous boards with the squares of T removed. And now this is great, right? Because I have 4 boards with one square removed of size 2 to the k. So by the inductive hypothesis, each of B1 prime, B2 prime, B3 prime, and B4, which already had a square removed, has a perfect tiling. Right? Why? Well, because these are boards of size 2 to the k by 2 to the k with one square removed. Right? So now the induction does something that seems kind of striking for me. It automatically fills in all of this stuff. Right? I don't have to even think about it. I just assume it's on the table. And now if I combine everything, I get a tiling of B. Right? So combining these tilings yields a tiling. Combining these tilings and T, right? And the one tile T that I placed. As desired. So that's it. That's the proof. Right. So the most clever part here, I mean, there are many clever parts in this proof, is probably this, I would say. You place this triomino T, and then here you know, the key induction step is this. Each of these things is of size 2 to the k minus 1 and has one square removed. Okay, so this is a very powerful technique. Because it sounds crazy, right? Yeah.
Do we need to prove that you can specifically tile PK with a that you can specifically tile it with a piece missing on the corner?
No.
Because we
no, because look at the statement. It says with one square removed, and that means with any square, right?
Oh, okay. All right, that makes sense. Thank you.
So there's another case of having the right induction hypothesis. If I had said the square has to be in the corner, I would have been in trouble, right? That wouldn't have worked. Because then my B4 might not have the square in the corner. It's really important that I have any square here, which is a stronger statement, right? Does that make sense? So yeah, let's take a, go ahead.
Wouldn't this proof require that the piece, I was going to say, wouldn't this proof require that the piece being removed be in B4, but I guess this could be rotated so that B4
Yeah.
isn't any of them, so the piece being removed could be
Yeah,
anywhere.
exactly. So that's where the loss of generality played a big role. That by rotating, you can, just for convenience, you assume the piece in B4. We could have done this another way. We could have said, assume the piece is somewhere, and then put the triaminal on the other three. That would have been an equally valid way to prove it. I just chose to write it this way because it's a little slicker. But you could write it that way. You could say, suppose the missing squares in BI, place the triaminal at the center in the rest of the quadrants. Okay. Any more questions? So this might take a while to sink in. The first time I was told this, I thought this was like cheating or magic or something. But I mean, it really is that powerful. The whole point of induction is it puts a lot on the table. And it really is hard to prove this not without doing induction. Okay. So now I want to move on to strong induction. Okay, so let's say what that is. So induction was this particular inference rule that I introduced here a while ago, which is that P of 1 and for every k, P of k implies P of k plus 1 implies that P of n is true for every n, right? Strong induction is a slight modification of this. So here's the inference rule. If you prove P of 1, and you prove for every integer, positive integer k, P of 1 and P of 2 and P of 3, ... and P of k implies P of k plus 1. Then the conclusion is that for every n in Z plus, P of n. So what's the difference here? The inductive step is different, right? So this is the basis step. And this is the inductive step. So what's the difference between this inductive step and the inductive step in the usual induction?
Our inductive hypothesis is stronger.
Our inductive hypothesis is stronger. We're assuming that P of 1 through P of k are all true. And that's kind of okay as far as this picture with the ladder goes, right? Because if you're climbing a ladder and you're at level k, you've already climbed all of the levels below that. So they're actually all sitting on the table. So you might as well use them, right? So that's all that's going on here. It's actually an immediate consequence of the principle of induction. So this follows from the sort of usual induction by taking a new propositional function Q of n to just be P of 1 and P of 2 all the way up to and P of n. So if you literally apply induction to that particular propositional function, you get strong induction. So it's not really a new thing. But the way the proofs work is a little bit different. So how do the proofs look? So if your goal is to prove the same type of statement for every positive integer P of n, how does the proof look? Well, so there again, there's a basis step, which is prove P of 1. And then there is an inductive step. And now here is let k be arbitrary. And now here's the difference. You assume not just P of 1, but you assume P of 1, P of 2, dot, 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 all the way up to P of k. So this is the change here. This is the inductive hypothesis. And then, okay, after you've done this, you do some stuff, you prove P of k plus 1. And then you eventually conclude what you wanted to prove. Okay, so it's a slight variation. Let me show you an example, which is something we've already actually done before, but it was extremely clunky because I did it before doing induction. I'm now going to give you a proof of the existence part of the fundamental theorem of algebra, which is very clean using strong induction. So here's the theorem, existence part of fundamental theorem of algebra. So if n greater than 2 is an integer, then n can be written as a product of primes. So this is the existence part of the fundamental theorem of algebra. And we sort of awkwardly proved it a few lectures ago. I really shouldn't have done that because I'm going to give you a non-awkward proof of it now using induction. I was basically doing induction without telling you what induction is. But let's now give a fully formal proof using induction. So we proceed by induction. So somebody asked earlier, can the base case, does it have to be 1? Well, what's the base case here?
2.
2, right? Because you start with 2. So the base case is, yeah, 2 is a prime. So the base case P of 2 holds. Okay. And now the inductive step. So assume k is now some positive integer bigger than 2. And now assume this is the difference. What's the inductive hypothesis? Assume P of 1 through P of k, i.e., every integer m between 2 and k has a prime factorization.
You have a P of 1 to P of k, but shouldn't it be P of 2?
Sorry, it should be P of 2. Yeah, thank you. Okay, so now this has put a lot on the table. So now we have to show P of k plus 1, right?
Can you scroll up for like 5 seconds? Okay, thank you.
So
Okay,
we will
question.
show P of k plus 1, right? Yes, you have a quick question?
Yeah. So in the previous induction method, we would
Mhm.
assume instead of P of K, we would assume P of K plus 1.
No, in the previous induction method, we would only assume P of K. In this one, we assume P of 2 through P of K,
Oh, okay.
right? So if we were doing regular induction, we just assume K has a prime factorization.
Okay.
But now we're assuming every integer between 2 and K. So all the previous ones have a prime factorization. That's the difference. Okay. Okay, well, let's show P of K plus 1. Okay, so K plus 1 is given to us. So what do? We have to show it has a prime factorization.
Prime, we're done. If it's composite, we can split it into two integers that
Yeah,
are each less than K
exactly.
plus 1.
So there are two cases. So case 1 is K plus 1 is prime. So P of K plus 1 is true. Just because it's the number is itself, it's a product of primes. And now case 2 is K plus 1 is composite, i.e. K plus 1 equals A times B for some numbers A and B, neither of which is 1, and neither of which is K. So for some A and B, which are at least 2, and at most K. Right, so first case is prime, second case is composite. So now, what do?
Factor A and B using the induction hypothesis.
Exactly. So now A and B are these numbers that are smaller than K plus 1. So by the inductive hypothesis, we can, the A and B have prime factorizations, and let's give them names. So we can choose primes P1 through P, I don't know what letter to use. Let's say PI, and Q1 through QJ such that A is the product of the P's, P1, P2, all the way up to PI, and B is the product of the Q's. Okay, so this was the key. And now, okay, we wanted a prime factorization of K plus 1. What do we do with these prime factorizations?
Multiply them together.
Yeah, just multiply them together. Right? Now observe that K plus 1 equals A times B equals P1, P2, all the way up to PI times Q1, Q2, Qj. And this is a prime factorization of K plus 1, right? So K, so Pk plus 1 holds as desired. Okay. Now, why could we not have used regular induction here? Like, what would go wrong if we tried to use the non-strong induction here?
We wouldn't have any way to show that A and B are equal to K. In fact, likely they aren't equal to K.
Right, exactly. So if we use non-strong induction here, then K being a product of primes is kind of a useless fact for us, right? Because K plus 1 is probably not equal to K times something. In fact, it's not, definitely not. That's why we needed strong induction, because we went from K plus 1 to numbers that are much smaller than k. But we can assume that the statement is true for them for free. That's the point of strong induction. So that's a rigorous proof of the existence part of the fundamental theorem of algebra. I guess I've proved it 3 times now, but okay, it's a good theorem. So I have to say, I mean, it's actually good to have multiple proofs of theorems. Like every proof, I mean, these proofs aren't that different, but every proof I feel like can really add understanding. And in math, often, you know, it's really good to have multiple different proofs of the same statement. But anyway, so so that's an example of strong induction. So any questions about that? Okay. I was going to do one more example, but I'm running out of time, so I'll just tell you to read it in the book.
I have a question.
Yes.
Can you prove uniqueness with induction?
Great question. I don't know. Let's try it. So what's P of n? I guess n has a unique prime factorization. So that means if you sort the numbers in non-increasing order, there's only one way to factor, right? Okay. So the base case. So again, the goal is to prove that this is true for every n bigger than 2. The base case is 2 has a unique factorization, which is true. The inductive step. Okay, so assume k is a positive integer and assume all numbers up to k have a unique prime factorization. And now there are again 2 cases. So case 1, k plus 1 is prime. This is sort of trivially true. And now the interesting case, case 2, k plus 1 is composite. Okay, so what are we going to do now?
Because it can still be split up into A times B, and A and B will be in the previous from P1 to PK. So
okay, so choose A and B between 2 and k, such that k plus 1 equals AB. And now by the inductive hypothesis, A and B have some unique factorizations. Let's call them P1 through Pi and Q1 through Qj. But now I'm kind of in trouble, right? Like, how am I going to prove that the product is the only way to factor k plus 1?
You multiply them together and like sort them, and you get a unique way of arranging them.
Why is it unique? There could have been multiple ways of choosing A and B. Right? So P1 through Pi times Q1 through Qj is a prime factorization of k plus 1, but why is it unique?
Doesn't the hypothesis or the theorem require that they be ordered from least to greatest?
Yeah, they could be ordered from least to greatest, but the non-uniqueness is coming because this choice of A and B is not unique, right? What if I did this in two different ways, A1, B1, and A2, B2? What's preventing me from getting two completely different factorizations?
Every prime is like, it has only one divisor, that one in itself. It cannot be divided by others.
Right, but k plus 1 is not a prime.
Yeah, but I mean, the prime factorization of A and B, they are like the only way of like the primes are arranged by the inductive hypothesis.
Yeah, for A and B, but not for k plus 1, right? Like, I agree that for A and B, these are the unique prime factorizations, but there's no reason for this product to be a unique factorization of k plus 1, right? We could have chosen a different A and B.
Is it that by the commutative property of multiplication, any other A and B that we would pick, we can just rearrange them and we would end up getting the same prime factorization?
That's begging the question. We don't know that, right? Why is that true? So the reality is this doesn't work. Okay, so this doesn't always work. So we used it for existence, but in this case for uniqueness, there's no, like, getting this to work is as hard as proving the uniqueness part of the fundamental theorem of algebra. So this is not a good strategy for proving the uniqueness part. At least not in this form. There is an inductive argument. There is an inductive argument, which is actually what we did in lecture 8, which is we used the well-ordering principle. We considered the smallest thing, with a non-unique factorization. But this particular form of the induction, I don't see a way to make it work because of the non-uniqueness of the choice of A and B. So that's a really good question you asked. Yeah. Anyway, I've gone way over time, so thank you. That's it for today.